Flame, and I'm Carl Christensen here with Cameron Christensen, Matt Christensen, Tim, the statistical anomaly Cox.
That I am.
We're going to today be talking about statistics, which so we're going to try to take kind of a useful approach on this. Hopefully, generally, our podcast is along those lines, given that it's supposed to be for the lay man. And as opposed to kind of the college take on statistics, we're going to kind of hopefully approach this from a more usable point of view, but we're going to try to give you a good background on what statistics are and some of the useful concepts and terms and ideas. So I think, I believe all of us, Matt and Cameron and I and Tim and I have all taken college level statistics classes, which kind of gives you a false impression of our statistical capacity. But
whatever, we're experts.
then we can't do this. Now, we're going to start with just kind of a generic understanding of statistics. So statistics, of course, being the study of recording events and then data and numerically, and then studying it in order to try to extrapolate information. So we're going to start a little bit talking about distributions. So distributions are essentially so you're going to get this data. So I guess let's start with an example. Let's start with just grades in school, because we've all had that before, right? So you've got 30 students in a school, in a class, and Tim here is grading their work. And as he grades, he's giving some of them A's, some of them B's, some of them C's, some of them D's, and hopefully not too many of them F's, or whatever your grading system is in whatever country you live in. As we have a worldwide audience, I'm sure everyone has a grading system that you can kind of map into the American grading system here. And so across this class, you've got your upper end performers, you got your lower end, and you got a large number of students in the middle. And so that, as Tim goes throughout his school year and is grading all these this data or all these assignments from these students, he's collecting more and more data, and so he can use this data, and he can and eventually what you can do is start using that to create what's called a distribution, or create a graph, and then as you plot these points, you're getting what's called a distribution. And so we're going to talk about, I guess, the normal distribution at first. And what is a normal distribution, Matt?
If you were to graph a normal distribution, say my values could be anywhere between 1 and 10, with an average of 5, then a normal distribution would be what we call that classical bell curve. It would start at 0, because there's no values that can be 0. It has to be between 1 and 10. And it would go up vertically in kind of a curve, reaching its maximum point at 5, and then it would drop back down to a low point near 10. And what you would find in a normal probability distribution is you'd have a whole load of values around 5, a smaller number of values around 4 and 6, a smaller number of values around 3 and 7, and an even smaller around 2 and 8, and then 1 and 10. One of the easiest ways to imagine normal distribution coming into play, is when you look at rolling 2 dice. When you roll 2 dice, the value that you will most often come up with is 7. That's the one that just has the highest probability of happening. Next to that, you'll have 6 and 8 as the next highest probable. And if you rolled the dice 1,000,000 times and you graphed how many times each value came up, you would have a distribution. Now, disclaimer, I don't actually know that a double dice roll follows a normal distribution, but it does follow that type of curve, similar to what a normal distribution has. Does that make sense?
I'd imagine, yeah, it does, and I'd imagine it would, but you're right. I guess I can't speak with any particular authority on the matter. But I do want to also highlight, as you were talking there, it reminded me that so in statistics, there are things called categorical variables and continuous variables. And so with my example, I was kind of giving what's more of a categorical variable, which is so categories. So obviously we're talking, A, B, C, D, E, F. Those are different categories. You can imagine if you're trying to also just, any type of putting people in categories, either by age or by a number of other metrics. Those are when you're starting to count those things, you're then getting categories as opposed to a continuous variable, like Matt said, 1 through 10, maybe not. But you can imagine as variables where you're counting income, for example. It's not like people fall on particular categories for income unless you bucket them as a choice that you make for your study or whatever. So there are different types of variables. But yes, for a normal distribution, you get what's normally your bell curve. And then you have what we call outliers on the edge, right? But there are very few of those. Vast majority of people, like Matt said, fall in the middle. And so that's your very basic normal distribution. There are a number of different types of distributions. We're not going to dig into them all that much. But Poisson is a distribution for, I believe, continuous variables.
It has to do with French fish populations.
Quite. Yeah, Tim?
Oh, and I was just going to plug in and just talk about a data set size. The larger your set of data, the more smoothly your graphed outcome will match up a classic bell curve. So if you have a small group of, say, 10 students, and you're graphing their performance on a standardized test, you could conceivably see a bell curve distribution, but you are much more likely to see a bell curve distribution if you have, say, 1,000 students with the results graph. The larger your data set, the more likely to look like that curve.
Right. Yeah, that's a good point. Sparse data sets, you're going to deal with not being able to see the whole distribution, and that's something that we could talk about actually for a while. Sparse data is something that generally you deal with in a lot of cases, and so then you're left wondering what kind of distribution you actually are modeling. But in this case, we're just going to kind of, I guess, deal with the ideal case where you've got a whole bunch of data and you know the distribution that you're dealing with. And so I guess actually before we move on from that, the idea that the distribution is great, right? But there are many cases where you're collecting data, you don't know the distribution, you're trying to model things like we talked about a number of podcasts ago with calculus. If you want to know your distribution, in order to do a model correctly, you got to know the type of distribution you're trying to fit here. And so having an idea going in, or what we call as a prior distribution, a prior model, is something that often comes into play. It's something I'm familiar with in the computer science world when you're trying to create models based on topic sets. So essentially I've got, let's say, 100,000 documents, and I'm trying to figure out what those documents could be categorized as, or what is contained in those documents. And so statistically I'm going through and I'm trying to group words together and figure out what particular topics are discovered or discussed in these documents. So, but before I go in, I might be dealing with some sparse data. I might not know exactly how to inform my algorithm beforehand. So what I do is I create a prior distribution. So I essentially weight particular variables already. And a prior distribution is really useful, even from the layman's sense, that often in statistics, you go in with kind of a preconceived notion. Something that you're already trying to fit the data to. And we're going to talk a little bit later about bias, and bias is a really big part of statistics. But it is prior distributions, prior information is really useful, even if you're not necessarily dealing with bias. So that's about all I had on distributions. So there are lots of different types, We won't dig into all of them. The normal distribution is very useful to understand, as that's how a lot of statistical graphs, those types of things that you'll see a lot of people understanding the word standard deviation, which maybe that's something we should actually deal just with for a second. Yeah. So Matt, what is a standard deviation? What kind of explanation can you give us of what a standard deviation means?
Standard deviation in general shows how tight your bell curve is going to be. Standard deviation, in the simplest terms, is the amount of values, the proportion of the values in your sample that are closest to that average point, or the value that comes up the most often, or the mean, or whatever. If I have some kind of data set and there's a 90% chance that my values are going to be between 3 and 4, and then only a 10% chance that my values will be outside that, I will have a very narrow bell curve, and it will be very steep and very tall, right between 3 and 4. My standard deviation will be low, because it means that the chance that a value deviates from that middle ground where everything is very low. So I'll have a very narrow standard deviation. If there is a chance that the value, let's say my value probability is wider, there's a 90% chance that my values are not going to be between 2 or between 3 and 4, but rather 90% chance that my values will be between 1 and 6. Well, my curve is going to be wider, and I'll have 10% of my values will be less than 1 or greater than 6, but 90% of them will be within that wider swath between 1 and 6. And so I'll have a larger standard deviation. More of my values will be spread out across a larger range. That's really what standard deviation is. There's different formulas to calculate it exactly and figure out what the standard deviation of the sample is. But in general, if you have a small standard deviation, it means that your values are more tightly clustered around some point. A large standard deviation means a wider variety of values.
Yeah, great. Thanks, Matt. That's a good explanation. If you see this, so there's a Greek character that often, that is used to designate what a standard deviation value is, and so if you ever see the Greek letter sigma, which looks like an O with a little line coming out to the right on top, that is your standard deviation. So you'll see like a value followed by that sigma, and
Sigma's
that's
an E.
Sigma what?
Sigma is an E.
Depends on the lowercase or the uppercase.
Well, right. Just what I've read and with the statistics, the Greek letter sigma, and what I'm seeing when you look at the standard deviation is looks like an O, but yeah. Anyway, it's useful to understand that as well. Like Matt said, there are formulas, and you're talking square roots of sums of means minus. Anyway, there's ways to calculate it, but really useful to understand, because then it helps you once again, understand how steep that bell curve is. And so I guess that'll move us on to a little bit more about some of the basic formulas in statistics. And so it's useful to understand the standard deviation formula, but there's also some of the other basic formulas in statistics that are, I think, really useful, at least to know what the name is and what they mean. So there's linear regression. So linear regression is one that comes up a lot. And as you can imagine, what we're talking about there is a line, thus the word linear. And you're taking all these data, this data that you've now essentially plotted, and you're now trying to fit a line to it. And so you may have seen these types of graphs before. So if you're trying to graph, years of schooling versus income, maybe you've got a graph where you can kind of fit a linear regression model to. And so the idea there is that as I'm plotting this data, it comes out on you can imagine your XY plot graph, and it's going up and to the right at the same time. Or alternatively, it could be a negative linear regression. It could be backwards, down and left. Anyway, but the idea is there you try and take that data and fit it to a line, and that will help you then extrapolate and say, okay, this is the data I had. This is the linear regression that I've done, which now tells me that my expected it tells me what I can kind of expect in the future. It also tells me how well my line fits the data, so how well my model fits. So if the data looks like it could fit a line, and then you put a linear regression model on it, and all of a sudden you come up with what's called an R value. So it's essentially what amount of the variance is explained by this line. Then if the R value is low, you're not explaining a lot of the variance. And let me try to explain that a little bit better. So once again, let's say you're trying to graph income versus years of higher schooling. There's going to be some crazy outliers, right? You can imagine someone like Mark Zuckerberg, who I think dropped out of college. All these high school dropouts or whatever that went on to be billionaires that are really going to skew things badly. I think a lot of the data will fit a line pretty well, but to what degree is the question, right? How well does the amount of schooling that I've had predict my income? And that's what you're trying to figure out, is what variance, how much is that variable, that predicting my income? And so as I do a linear regression model, it's going to tell me, okay, yeah, I'm accounting for, let's say, 60% of the variance. So my R value, if I remember this correctly, is that my R squared value is going to be 0.3. And so that's going to tell me that is statistically significant. And that's another really useful term. Statistical significance tells me whether or not the data I have and the model I've got are actually explained by chance. Is this something that could just, a small data set, all of a sudden I now have found out something that isn't actually something that I can extrapolate further, and that's then going to be not useful to me, and that's statistically insignificant? Or is this statistically significant, meaning I've got enough data, like a large set of data, or a model that fits a smaller set of data quite well, and in which case it's going to say, okay, this is statistically significant. And that's what statistically significant means. It is actually a mathematical term, meaning what is the probability that this data and the model that fits this data is just done by chance. There's a probability assigned to that, the chance there, and if that probability comes out to be significantly lower, usually the threshold is 0.05. If the probability of something is less than 5%, 0.05, then it's said to be statistically significant. There are different thresholds, but that's, I think, the one you're going to see most often. So yeah, linear regression, really useful. And also, obviously, the idea of statistical significance. Let me open this up a little bit. Statistical significance also, there's more that could be said here. Matt or Tim or Cameron, any other formulas or comments on statistical significance that you want to share?
It's 95%.
Mm-hmm.
Right. Tim?
I'll just put out, since this has been a little heavy, I want to lighten things up a bit. 3 statisticians went bow hunting. They see this huge elk. The first one lines up, takes a shot, misses 10 feet wide to the left. The second one lines up, takes a shot, misses 10 feet wide to the right. The third one starts jumping up and down. We got him! We got him!
Oh, boy.
There you go. That's all I've got to say on this.
Good. I like that.
Okay. Yeah. So nothing else on linear regression, Tim? Statistical significance that actually, is significant?
Ooh, that's a statistician's dig right there. No, I think you explained it fine. it makes sense. It's a useful thing if you're looking at any data set and trying to see if there's a pattern or not.
Right. Right. Let's see. The other formulas. So it is useful to understand that there are lots of different models that people use to, and different data and different types of data require different types of models. There's what's called t-tests. There's one tail or two tail or t-tests, and we're not going to dig in too much on t-tests. Essentially, it's just different ways to model the data and come out with probability of a particular event, and once again, a model, an explanation for the data. So
You
there's
just
lots
don't know how to read tea leaves very well. It's okay. You can be honest.
tea leaves, t-tests, slightly different. I guess it really depends on how well you understand a t-test. But there's lots of uses for these things, and maybe Tim, I think you've got some anecdotal. Maybe you can tell us actually a little bit between anecdotes and statistical significance.
Yeah,
or statistics. Yeah.
Yeah, absolutely. And I need to full disclosure. I dug a lot of these examples out from my college stats book, which I reviewed just a bit. But great examples. Here's one for you. Years ago, there was a debate or argument about, do power lines cause leukemia? And they did big, long 5-year studies, millions of dollars on it, and determined after looking at it all very carefully that there was no statistical connection between power lines and leukemia. In other words, living near a power line is not going to increase your odds of getting leukemia in any way that can be statistically measured. However, that that finding was published in a academic journal, but at the same time, you have people who are getting interviews on, say, a local news program and talking very passionately about how they believe that this is a problem. And you imagine just your typical person going throughout the day, which one is likely to affect their opinion more? Even people who are uncertain, we as humans, we tend to warm up to stories. Stories are persuasive. It doesn't mean that every story is false, but a lot of times one story can either be a statistical outlier or just outright unsubstantiated. And one anecdote can sway people's opinions, even when statistically speaking, there's nothing going on. And it's awfully hard for us to kind of step back from the emotional response to an anecdote and ask ourselves hard questions about statistical significance, reliability of data sets, the source of the data, how bias plays into the results, and so forth. There's a lot of question marks, and a lot of times we're not paying attention to those when we're evaluating information that goes around on Facebook or Instagram or even in the nightly news.
Yeah, that's a good. Thanks, Tim. Yeah, so that is really important, especially these days. We got lots of data out there. The internet is great for being a tool to disseminate data and information, but then it's very important that you understand, some of these statistical rules and what anecdotes are. So that, the idea that a narrative, like Tim said, can play really well, but that's very different than having statistical measurements and being able to show with numbers and data and math that something is true. So,
and then on top of that, you have to be wary even of statistics themselves, because they can be employed in a whole lot of ways that are not reliable. Another example.
I heard a great anecdote that I'm sure is true, that 90% of statistics are made up on the spot.
I heard it was 25%. So,
well,
whatever.
So as a thoughtful person, I'm going to just presume that it's an average of those two.
Right. You were saying
the anecdote that I'm going to, or this example I'm going to share is not too far off from that. A headline read in, this was based off of I think a advice columnist's, survey, but the headline that ran was 70% of parents regret having had children, and that was their results from this survey they had run. But if you stop and look at the data a little more carefully, if an advice columnist puts out a question and says, write to me whether or not you regret having children, well, who's going to be most likely to respond to that? You may have a handful who absolutely don't regret having children, and some who, I don't regret having children. But the most likely responders are going to be people who are passionately, maybe they've been wronged by a child or had some kind of dramatic falling out, and they're very upset about it, and they're going to be more highly motivated to respond to this. So we have a case where we have a data set, but it's just not, it's a poorly conceived survey in the sense that it's not going to yield us a real result. A carefully constructed survey that was planned and designed to capture parents of all sorts and truly of a random assortment of parents yielded results that said 90% of parents do not regret having had children. So compare the difference. 70% of parents regret having children versus 90% do not regret. That's a drastic difference. So when you see things out there, you have to be careful. What's the source? How is that information obtained? A lot of times corporations will hire experts or statisticians or scientists to conduct studies. Well, are those studies really reliable, on the benefits and detriments of sugary drinks if the study was funded by Coca-Cola? There's so many things to watch out for, in so many ways that our opinions and our knowledge of the world is manipulated by people using statistics.
Yeah, that's a really good, important, and that's something we need to underscore. So this is, I guess, what I was talking about in the beginning, where we want to make sure this appeals to a lay audience. We want to make sure that you understand, statistics can be used in all kinds of ways, and I think everyone knows that. But understanding the underlying principles around statistics can help you tease out truth, because just giving up on statistics is also very problematic. So just saying, to heck with it all, somebody's lying, and I'm gonna, and then you just pick, that's problematic. Somebody out there has truth, and you just have to tease it out so by finding out kind of the math behind it, the selection bias. So we'll talk about all the different types of biases in a second, but
a quick kind of shortcut to that is to just check in with us here at Learn It From a Layman, and because we're thoughtful and reasonable, and we'll always tell you right.
Exactly. Appeal to authority. There's the anecdote, the quote that goes, there are three types of lies. There are lies, damn lies, and statistics. So you need to be very careful when you're looking at statistics, like Tim's story just showed us, the number of parents that regretted having children. But you also need to be aware that there are true statisticians out there that do a darn good job, and that so you need to just be able to figure out where the data is coming from, where the biases could come from. So jumping really quick back to formulas before we move on to biases and those types of things. I mentioned the t-test, and before I move on from that, I just want to tell you what that is. So let's say Tim teaches at a school. There's another school, let's say Tim's rival school. Let's say on standardized tests, Tim's rival school outperforms Tim's school by 10 points out of
lies.
So now we've got this population of students, we've got all this data, and then we've got the population of students in Tim's school, and we want to figure out, are these statistically different? Like, is Tim's school statistically significantly not performing as well? And the t-test is how you're going to tell that, right? The t-test is the formula of being able to tell, okay, given this formula, this population and their numbers and this population and their numbers, I'm going to be able to tell you, okay, are the means different enough given the number of data points that I have to say, okay, this actually is a meaningful difference. So that's what kind of a t-test is used for. And they're different. There's, like I said, single t-test, two-tail t-tests, but we won't go into all those specifics right now. But let's move on from those kind of formulas and talk a little bit about correlation. So correlation, maybe I'm assuming most people here have heard the phrase correlation is not causation. Matt, what can you tell us about correlation?
Correlation is the idea that two events are somehow linked together. One thing happens, another thing happens in parallel or at the same time. And you see these linkages all over the place. Sometimes there is a cause and effect link between two things. Sometimes there isn't. Sometimes the cause is separate and the two effects are maybe caused by the same thing, but they do not cause each other. So, for example, someone comes down with a viral disease. The next day, you notice that the viral disease is affecting a number of people in that same person's neighborhood. Now, depending on who you ask, they will tell you that there is a causation effect there. Your reasonable health professionals and anyone who's not a complete nitwit will tell you that, yeah, there is a causation effect. This one person affected these other people, and that's what happened. Now, your COVID denier will say, no, it's totally unrelated, and that correlation and causation are not the same, even though in this case they may very well be. The guy was walking around without a mask, breathing on everyone, but that doesn't mean that that's the reason that those other people got sick. That's kind of an example. There are places where correlation and causation are legitimately not related. Turns out that the I'm trying to think of a decent example offhand. Okay, the supply of nacho chips and the supply of avocados in my house, they tend to go down in parallel. The reason is me. I'm the cause. I make guacamole and I eat the nachos with them. But the fact of nachos being eaten does not cause a diminishment in avocados, nor does the fact of avocados being consumed cause a diminishment in nachos. The root cause is a factor that is completely separate. It's the fact that I get hungry and I eat both. There is a correlation between the diminishing supply of nachos and avocados, but it's not a cause and effect relationship. The cause is something separate, and the cause is me. I'm causing both of those things at the same time, but it is not the two things causing each other. Does that make sense?
Yeah, I've got another example. Yeah, it does. I've got another example that I think people are very familiar with. So the idea of autism, the number of autistic people, and that's climbed significantly, right, in the last couple decades, versus number of immunizations. And so you can create a very nice little graph that shows as the percentage of immunized population goes up, autism goes up. And then you say, okay, well, clearly immunization causes autism. Well, that's been thoroughly debunked. And if you care to Google it, you can find, well, actually don't Google it because you'll find all kinds of garbage, but it's just not true. And you can find that in lots of different papers that are created by
actual peer-reviewed sources.
Right, exactly. Peer-reviewed sources by wonderful statisticians and mathematicians and doctors that have debunked that thoroughly. So it's not the case that is that autism is caused by these shots, but but you can create a graph that makes that correlation, right? And so that's an example of correlation, not causation. So obviously they have independent causes, right? People are becoming immunized more and more in order to fight disease, and more people are being diagnosed with autism, and that there are reasons that that could be the case. More people going in, us understanding autism better, more people having availability to doctors that are able to diagnose them with that, and there might be other factors that actually are causing a percentage increase in autism in the population, but it's been determined and clearly that the cause of autism is not immunizations. So that's an example of where correlation is not causation. Tim, you said you had an example as well.
Yeah, well, and I just, based on all of this, what do we do? Because can you get real muddy? The thing to do is to look for what they call the lurking variable, that behind the scenes variable that hasn't been considered. And I'll give you one example of how you can do that. Let's say a music camp posts an ad or sends you a flyer or something trumpeting the fact that kids who take music perform 25% higher on aptitude tests and so forth. And they present that as a reason why you should get your kid into music. And now the music's dear to my heart. I love music and do music and stuff, but there's a lurking variable here. The flyer is implying causation when in fact we can find a lurking variable that is the real cause of this correlation. In this case, socioeconomic status. So kids who are richer are more likely to be enrolled in some kind of music program. But socioeconomic status has been shown to have a direct impact on performance and test scores for a number of reasons, like nutrition, access, and so forth. There's a whole bunch of stuff, but in this case, socioeconomic status is a lurking variable, and while music is great, the contention that it causes or on average a 25% improvement in performance on tests is just not the case. So always ask yourself what could be going on behind the scenes to create this pattern, and it's not necessarily going to be one causing the other. Good rule of thumb, things are often more complex than they appear, especially if what appears is being presented by a party with a vested interest in your opinion. In this case, the music camp has a vested interest in my having a high opinion of music.
Right. So this underscores once again the idea that you need to look at multiple sources for your statistics, right? You need to I also love music, and so I'm partial to those types of studies. But then you have to look and say, okay, well, are there other things involved here? Is what percent of this variation is actually accounted for by this? Are they looking at all the potential variables, like Tim said? So so let's talk a little bit about really quick break from the hard statistics stuff. I want to thank our Australian audience again for showing up last month. Good job.
I do want to note that Australians have been experimentally proven to be statistically cooler and awesomer than people from many other locations. So,
Tim, you're offending all our other listeners.
Well, Carl, we got to go for it.
Yeah, Tim and I were talking about this the other day, actually. If we can just get a large enough Australian following and go on tour in Australia, our podcast will have been a success. So
all you Australians out there, we're going to shamelessly pander to you from now on.
Not like we don't appreciate all the Canadians and the people in the UK. And I guess our fellow Americans, I appreciate you as well, given that actually you're still, by sheer percentage, the largest number of our listeners. Anyway, whatever. But I appreciate our audience continuing to grow. And so hopefully this is going to be also something that you find interesting. If not, we'll have Tim sing and dance at the end. So the dance will be significantly less interesting given that this is a podcast. Okay.
But it will save everyone too from having to see me dance, which thank goodness.
That's true. Yeah, that's okay. So moving back to statistics, I wanted to talk a little bit about conditional and independent probabilities. So statistics. So I guess once again, starting with an example here. So let's say Matt is going in to take a test. Cameron. Let's say Cameron's going in to take a test. Cameron, I believe, most recently graduated from all of us. So Cameron's going in to take one of his finals, and we're trying to figure out what the probability is that Cameron gets a perfect score on his final, right? 100%. The independent probability of that, right, is just a measure of how students generally perform on a test, on maybe even that test. And so going in, we can know what the independent probability is that Cameron is going to score perfect on this test, and probably pretty low, right? But let's say then
I never studied, so yes.
Okay, so there you go. Perfect. Now we've got a condition. So now we've got this, given the condition that Cameron has spent 0 time studying, what is now the probability that Cameron scores a perfect test score? And now our model and our probability has dropped precipitously, right? Whatever it was, say it was 1% before, now it's 0.001% if without any studying. But the number of conditions that can also come into play, right? Let's say Cameron in this class currently holds a 100% grade. So now the probability jumps back up significantly higher than it was before. So preconditions influence the probability of an event, right? And that's really important to understand also. So independent of the independent probability is just the probability of an event given no prior data, and once we have conditions, so if we can meet a condition. So for example, once again, another example in the area I'm familiar with, so with language, so the probability of the word potato, right? Not particularly high in any given sentence, but let's say that the word Idaho precedes it, or au gratin, right? All of a sudden, the probability that the next word following au gratin or Idaho is potato is a huge percent higher than it was before, right? And so those are some of the conditional probabilities that are really useful to know. So an important concept in statistics is understanding conditional probability and how that affects the outcome or the expected outcome. So,
Carl, I want to know how often au gratin isn't followed by potatoes, by bananas or
Okay, there you go. Exactly. I have no other word that could potentially follow au gratin. So I guess 0.
Anyone who tries au gratin bananas, send us your results and let us know how it goes.
Okay. All right. So let's move on to I think Tim might have 1 or 2 other things to discuss, but I wanted to discuss bias. And we've already Tim's brought up bias in a few cases, but maybe Matt and Cameron can also share some of the bias that either anecdotally they've seen in statistics or particular bias, given statistical bias measure or rules that you can watch out for. Cameron, any statistical bias that you're familiar with, things that you've seen maybe?
Bell curves are bad.
The what are bad?
Bell curves. I
Bell
hear
curves
all
are
the
bad.
time, like, people like bell curves are bad or don't grade on a bell. I personally think grading on a bell can be good, but I don't know. Then again, maybe not.
So that's your traditional understanding of bias. That's so people can be biased against a particular. And people, as we already mentioned, people can be biased against statistics if you have become a bit jaded by wrong statistics or things that you view to be wrong in the past. But there's a particular idea of bias in statistics that is important, that kind of has its own meaning, right? And Tim brought this up. And so, maybe, Matt, are you familiar with any of the statistical bias that exists?
Well, unfortunately, I'm not offhand. I would have to either look that up or tune into an appropriately informative podcast to remind me what those biases are.
So let's say learn it from a layman, for example. Okay, Tim already brought some up, so maybe Tim has one or two more. I've got a list here, but Tim, did you have
Why don't
any tips?
yeah, why don't I'll share what I just barely looked up, and then you can fill in the cracks. There's sampling bias, non-response bias.
Sample size. That was something I really needed to cover, and I think you already brought it up a little bit, but let's take another minute or two to talk about sample size and
Oh,
or
yeah.
samples and what that is before we dig further into bias. So let's take an aside real quick, Tim. What is it? Before we talk about sample bias, what is a sample?
Okay. So sample is your collection of data. If I want to know, if I want to know about the dogs in my neighborhood, my sample size would be how many dogs I observed or was able to get data for. If I was able to get data for every single dog in my neighborhood, or was I only able to get data for half? Let's say I'm surveying, people. Are dogs too loud and noisy? But if I send it out as an optional survey, I'm going to have sampling bias. Oh, sorry, we're talking about sample size. Darn it. If I want to know, are dogs a problem in our neighborhood? Are they too loud? And I only sample the people in my neighbors next door, either side, in front of me and behind me, and then my sample size is too small, and I'm not going to get a good picture of what people really think in my neighborhood. I'll also be more prone to problems, like, for example, perhaps I or one of my neighbors has a really loud dog, and so our sample, because it's too small, is going to be skewed from that, and we're not going to get any response from the neighbors farther down the street who aren't close to that noisy dog. So a good study or a good survey or whatever is going to strive to get as large a sample size as feasible, and recognize that the larger the sample size, the better, clearer a picture we have. It's kind of like focusing a lens. A small sample size is just like an unfocused lens. You might be able to capture a bit of what's going on, but the bigger your sample size, the more you're focusing the lens, and the closer you're approaching clarity.
Yeah,
does that make
that's
sense?
Perfect. Yeah. So yeah, the idea, yeah, right, exactly. You're trying to, with statistics, you're trying to make judgments on about a particular population, right? You're trying to actually make judgments across something, models or whatever, that you can then extrapolate data and say, okay, I know that this is true. Well, like Tim said, if you have, so you're trying to get a sample. In general, you can't sample the whole population. You can't get everyone, and so you just have to make sure that it's representative. Because you can imagine, for example, you go to the store. Because this is the word sample outside of statistical means. Let's say you're trying to get a sample of a cookie, right? But you have this very large cookie, and at the bakery at the store you're going to, and you ask for a sample, and they cut off the one tiny burned portion and give you that as a sample. Is that a representative sample of how the cookie tastes? It's not, right? And so that's what the idea in population, the population sampling, is if you don't get kind of a nice clear crosscut of the population that will actually give you the whole flavor of the cookie, proverbially in this case, then you're not going to actually be able to say with any particular meaning how the cookie tastes. So you need to be able to create a sample that is meaningful, that will be able to extrapolate and create meaningful models. So yeah, go ahead, Tim. So that's a sample. Back to biases. You said sample bias. What else?
Yeah. So sample bias. You've got non-response bias, response bias, question order bias, and those I just looked up, on Google, statistical bias, and those are four given types of of bias in a sample. So, we could talk about one of them or maybe more than one. Are there any that you have examples for?
Yeah, well, I mean, those are some good ones. There's one that, as I was ready here, I thought was interesting, but there's something called survivorship bias.
Oh, yeah, that's an interesting one.
Yeah, that is interesting, and it kind of, I mean, the way I understood it as I was reading through it is this idea that, let's say I'm trying to understand what, get what factors or health factors predict cancer or cancer survival, or cancer, what being diagnosed with cancer, and so you start collecting data from people that have had cancer. Well, obviously, by definition, you are now collecting data from people that have survived cancer, unless maybe some portion of the sample are people that currently have cancer. But that's the idea of survivorship bias. Is you're obviously not going to get the people that have not survived. And so the sample that you're collecting might not be representative enough to be able to tell you, okay, the people that actually end up passing away because of cancer have a particular health background or genetic background that would inform your model significantly more than the data that you are collecting. So things to watch out for, and that's one type of bias. Tim?
And just to put out that this kind of stuff comes up even when we're not talking about technical official statistics stuff. I see the survivorship bias come out when I talk to my junior high school students about the careers they want to have. And a disproportionate amount want to have careers in professional athletics. A lot of kids want to be a baseball player, a football player, a basketball player, or whatever. And their influence is, or their preference for that is influenced by not recognizing survivorship bias. We see on TV, the very top of the pyramid, a few hundred of the highest paid professional athletes. And so the impression is that, oh yeah, baseball players, they get paid millions of dollars, and basketball players and football players. The reality is our view is affected by survivorship bias. The only ones who get any screen time on television, in games and so forth, are the very small portion who have had the incredible talent and good luck to make it there. What we don't see are the thousands of minor league baseball players and thousands more in any sport who tried and didn't make it. So it's a form of survivorship bias. We don't recognize that the vast majority of professional athletes are actually, impoverished. And anyway, so it's something to pay attention for, even when we're not talking statistics. These things are still, it's how we view the world, and recognizing the biases and the ways that the information we receive are skewed or stilted.
Right. Yeah, the word skewed, also a very important statistical word that I don't think we've covered as much, but a skewed model, one that is then no longer normal, but actually fits further out to one side, so that you're looking at a what's called a long tail, right? Generally, that's a skewed model. And so, yeah, the idea that if you're looking at professional baseball players and not counting all the other types of baseball players, your idea of what a baseball player makes could be very skewed. Okay, Tim, other types of biases before we wrap up here?
I think we've covered the idea there. Do you want to talk about blind and double-blind experiments, or is that a little too far?
Maybe just kind of the idea briefly about, very briefly, we can cover that.
Okay, and guys, you can correct me if I'm a little off on this, but there was a guy who believed he had a horse who could do math, and so he took this horse, and it was incredible how well this horse could, by stomping its foot, could respond to numbers and problems and stuff, and it was just blew people away. And the horse did it again and again. But what they found was when they removed the horse's owner, the horse couldn't perform. The outcome was influenced by the desires of the person running the experiment. You see this with other things where people would try to guide the hands of someone who's lost their control of their hands, and to see if they could make them type something, and they would type these beautiful messages, but it turns out that the expectations of the people holding the hands were influencing that. The Ouija board, oh, you're going to make it say something creepy. It may not even be someone's intention, but if it's their expectation, it can influence the results. And so when an experiment is conducted, it's important that the best setup is double blind, where not only is the person being studied blind to what's going on, but the person administering the study is. So here's an example of a blind versus double blind. If I want to do a study about, does this medicine help with this condition? If the person receiving the medicine knows whether they're receiving the medicine or a placebo, that's going to affect the results. And if they know they're getting the medicine versus not, their improvement, so-called, may just be a result of their expectations of improvement. So we don't tell them. Some receive a placebo, some receive the actual medicine, and no one knows what they're getting. That way we can see what's really going on. But to make doubly sure, we also have the person who is delivering the medicine to them not know what they're receiving. That's the double blind. That way they can't betray in their manner of giving the medicine or whatever, influence the results. And so anyways, these are examples of how tricky it can be to get truly unbiased results, and how carefully you have to set something up if you want to have a result that really gives you the truth.
Yeah. Thanks, Tim. I think that's important. And I think that's a good way to finish the podcast here. Is statistics, one particular study, one particular, even well set up statistical study is not the end of the story. Generally, there are, as time progresses, more studies are done, other variables, other factors, other things come up, and so it's really more the progression of a statistical study through time that really helps you understand what's going on. And so as you are trying to wade through all the data out there, just make sure that you follow the timeline, that you stay updated and aware of what is being studied, and if these studies are done well, and like Tim mentioned, also Matt mentioned, where the studies are coming from, who's got a vested, if you're being told all the benefits of dairy, and it's all funded by the Dairy Council or whatever, then let's take it with I'd say grain of milk.
A grain of custard.
Okay, there you go.
Or a grain of curd.
Yeah.
There you go. Yeah.
Regular curd.
There we go. Yeah. So just I really have appreciated my statistical knowledge, my statistical knowledge as it is. That helps me inform myself as I read articles and try to figure out what's true. So let's encourage everyone here to just study up and be familiar as you're trying to figure out what to believe out there. And if you don't know, we will tell you as the laymen that are possessed of all the facts. So, okay, let's say goodbye for today, and we will see you back, especially all of you Australians and some of you other people soon. And until then, stay safe.